Welcome back to Element 14 Presents. I'm Clement, I'm a gearhead, which means I love having the right tools for the task. And this time, we're making one ourselves. Usually, I don't show you the finished piece at the beginning, but this time I have to, because in this case, the case is integral to the functionality of the device. Let me explain. This here is an ESD detector, which means it can detect lightning with an antenna. So you put an antenna here, you extend it, and then you can detect lightning that has happened around you. And then you can basically trigger stuff based on these lightning events, like cameras, for example. But that's not what I'm using it for. For me, it's a real ESD detector, means I want to detect electrostatic discharge events and then correlate them in time and amplitude and whatever to other events. So I use this as a debugging tool for electronics development. So ESD events can be quite different and difficult to detect. When I turn on my device, I usually should now be able to detect ESD events like this igniter. What it does is basically it throws a little spark, and that spark will get detected by the antenna. And with the antenna variable in length, I can basically adjust the sensitivity so it will detect from further away or closer by. And you can see there are two things lighting up here. We should talk about the circuits to understand what these are actually doing. Wait. So why do I even need to detect ESD events? Basically, ESD or electrostatic discharge can come in various forms and it can disrupt your electronics projects. So your device might get damaged or not work as intended, or it may have glitches or whatever. And if you experience that, you should know where it comes from and if a glitch is dependent on such an event or something different. And that's why I'm building a dedicated device for that. So I'm sure that it's actually ESD and not me messing up or something else going around. It's called electromagnetic immunity, which is something that you have tests for when you want to sell your stuff, because it actually has to be immune to that stuff. This is where the case also comes in. Ooh. So we have a circuit that goes inside a case. You can see this is specifically made for that case because we need a special kind of case for this project. We're dealing with high voltage discharges. So in case a discharge event happens, it would also affect the circuit we're using in our project. So that means if our test equipment is affected by the thing we're testing, we're not really testing, we're basically hoping it survives. So we need these special cases. These are made by Hammond and they are EMI shielded, which means they have gasket and special end plates and whatever to make sure that no electrostatic discharge comes inside and gets out of here, and no EMI events would disturb our circuit. So that's why the case is this time integral to the design. It's also like directly connected to it. Let's look at the case, let's look at the circuit in KiCad. Welcome to KiCad. This is the circuit of our project. We have a few distinct parts to it. So this part over here, that is the original Wenzel detector. It's a design based on a public domain design by Charles Wenzel. I had to adjust some values in my actual assembly because I just couldn't get the parts with the exact values, but they seem to not matter that much. This 82K resistor, for example, I've used 100K and it still worked. And also I didn't have a 1K here, so I used, I think, a 2K. So it still works. I think the other components are much more critical. So what does this thing actually do? The most important bit is that we get everything here in frame. So here is the antenna connector over a coaxial cable or a coaxial connector basically. The outer end is connected to ground for shielding. The pin, the actual antenna, goes into the circuit. There is now a capacitor and a resistor to ground, so this capacitor gets charged, and also there are inductors here. So charges cannot only be stored by capacitors, but also by inductors, especially if it's AC based, then usually inductors are much more common to be used. So all these do is they build up enough charge from these high voltage but very low current ESD events to charge this tiny capacitor. If that tiny capacitor, which will have quite high voltage but very little current, it gets basically with this voltage divider brought to a safe level for this transistor. But this charge will be enough to trigger that transistor. And if that happens, that means we have detected an ESD event. And the second stages of transistors, which is a Darlington pair, those will also get triggered once this capacitor is charged enough. So there's basically, this is a multi-stage charging process that allows finally the last line, which is this one here, to be discharged because they're pulled high to 5 volts. So this will get pulled low whenever there's a high enough ESD event detected on this side. So it's charge up this stuff, translate it into a voltage that can trigger this transistor, which will then allow this capacitor to trigger this transistor, and then they trigger this transistor, and in the end what it will do is pull down this line. So you get an actual pulse in a 5 volt logic level domain, or 5 volts like voltage level domain. It's not really logic level. So it's safe to connect other stuff to it. You wouldn't like to directly shoot the pulse into your other circuitry because it then blow up your stuff, or it will be too minuscule to even trigger anything. You want to get it to a level that is safe enough in voltage and current, of course, but also strong enough that it will actually trigger whatever you're trying to trigger. This here is just voltage conversion from two AAA batteries to 5 volts. So we have a stable 5 volts. There are a lot of versions of the circuit for other voltages, which can be more sensitive to these events, have different levels for triggering other types of equipment. I specifically got with 5 volts because I want in the end to have a safe output level for triggering other devices. This is the analog part of the circuit. Then we have a digital part, which is in its simplest form, basically this triggers an output. And also this pulse is directly connected to a coaxial output, so you can get the raw pulse just converted to a safe level, but it's the actual pulse waveform. And this other output is then a true logic level output. So it's controlled by a microcontroller, and it gives you a real 5 volt or 0 logic level. So whenever there's an output, this will be put low, but we can also, since it's microcontroller controlled, we can just change the code to give us a high level whenever it's high and a low level whenever it's low, or change it around however we want to use this device for our purposes. So the microcontroller could be just a logic gate or some analog circuitry, but we specifically chose a very tiny, it's an AT tiny microcontroller, so we can control how it's outputted based on our application. So we have the choice even after we've built the circuit. Here is the microcontroller. It's an AT tiny 412. Why? Because it's super tiny, super cheap. We just need a few pins. It just has enough pins for our purposes. One thing that I would change for a second iteration is I have here my programming header, and I have a spare GPIO, and there's TX and RX on there. I could use now this RX pin, this output pin for programming the microcontroller if I wanted. And yeah, maybe there's a better way to even allow for UART communication over one of these BNC ports. Yeah, it's a thing that might get implemented in a future iteration. Could make it even more useful. Then we have an audio indicator. This didn't work. So for some reason, I couldn't get like right sounds going on an ATtiny. If you know why, maybe there's some issues with the timers and stuff. I'm using Arduino to program it. Maybe there's some limitation. Let me know, or maybe you know if the circuit has an issue. Post it on the Element 14 community and educate me, please. There might be just an issue with the circuit. I hear it clicking, so it clicks. Or maybe the buzzer is the wrong type. Could also be, or the voltage level, or whatever. There could be a lot of reasons. Yeah, we also have two LEDs. One is also directly connected to the pulses, so it actually lights up only if the pulse is high enough to illuminate an LED. But it's pulse is basically pulling low enough to illuminate the LED. The other one is connected to the microcontroller, so it's also microcontroller controlled, and we can say make this flash when there is a signal, or make it flash when there's no signal, whatever you want. With a microcontroller, again, we have the flexibility of just reprogramming it if it doesn't fit our needs. Now we also have this design here, which is the actual PCB design. This might seem weird to you, these connectors. We're using panel-mounted BNC connectors. Yes, we do, but these footprints are for SMA connectors. And if you would like to assemble that with SMA connectors, if that is what you prefer, you just put them in here and they work exactly the same way. And there's nothing stopping me from just wiring my BNC connectors to these points as I did. Also, we have some nice AAA battery holders here. You could also substitute these with a different type of battery. I just chose these for convenience so they fit into the package. And very importantly, look at all these stitching vias. There's a ton of stitching vias here. This is because I don't want any crosstalk between all these planes, so I make sure that everything is basically shielded by a ground plane and have them closely stitched. And these is a random pattern because I have no clue about the frequencies. I have no clue about the types of events I'm detecting. They can be very different. So I'm not calculating my via distance based on the frequency. I'm just going for a random dense pattern in hopes that I will cover most of them. This is the chaotic approach to EMI. You might want to consider this unprofessional, but guess what? If you're doing professional stuff for EMI stuff, you will run into the point where calculating the exact frequencies is not possible anymore because you don't know them, and then this is where you resort back to chaos theory and just see if it works. And in this case, it seems to work quite well. Yeah, also had fun with the logos. The analog part of our circuit is based on a public domain design by Charles Wenzel. Why is it public domain? Because I asked him to specify it. This design has been published in numerous places with or without consent. Basically, nobody really asks him for permission when they just see stuff online. But the fact is, on his homepage he didn't state a license, and if you can't find a license for a design you're using, you should always ask the original author. And first identify the original author, because other people might pass off stuff they stole as their own work. So if you haven't seen like an explicit license with terms and conditions you can use a design under, ask the author for permission. This is what I did. And he told me this design he considers it public domain. I give attribution to the original creator. That's why I also specifically call this part of the circuit, the Wenzel detector, named after its original author. And I want everybody to know that this design has an origin, and a really good one at that. Also check out his webpage. It's full of really good analog circuitry for various purposes. So I want to give a shout out to all the people who post their stuff online and basically let the community go with it. Please put a license there so people actually know some terms and conditions. And if you find something online, you want to use it, and you don't see a license, please ask the author. I think this is really important. Now that we know that our circuit works, we can just turn it on and now determine if something might issue some ESD stuff. This motor seems to be relatively safe, but others might not be. Ooh. So let's do some practical examples. So let's say we have some corrupted signals on a cable and we don't know why this is always glitching. Well, if we use our ESD detector as a trigger for an oscilloscope, we can correlate ESD events and the glitches on the signal line in time. If the ESD event happens, the oscilloscope will trigger. We just use the one-shot function, basically. And then we can see the other line at that specific moment in time. And turns out, with a second trace on the oscilloscope, we also can correlate the exact ESD event, like its waveform, to the actual event happening on the line. And if those correlate in time, there's a very high chance what we're seeing is ESD coupling into our data line. Because ESD events can be very sporadic and like pretty much unpredictable, it's important that we actually detect them when they're happening and not like looking for periodic occurrences. Periodic occurrences usually more, they tend to be more affiliated with other events happening at the same period in your system. So maybe it's your clock, or maybe it's an event that's get triggered by a time loop or by an interrupt that happens periodically, maybe like for rotation sensors or something. Or it could be the stepping signals on your stepper motor driver, or it could be even the motor lines themselves, especially if they are activated periodically. But usually discharge events like firing on a motor, electrostatic discharge from rubbing, or from other events like capacitive coupling, like when your device actually acts as a capacitor, it builds up charge and then suddenly, because you touch something, it just discharges. That is usually very sporadically and not predictable. So you have to actually detect when it happens and at the same time look at the rest of your circuit that you're debugging. In the beginning, I told you about the importance of this case for the whole project. We have to also integrate all the connections correctly into the design. And of course, the end plates are basically the places where EMI gets in and out. Not EMI, ESD, like charges get in and out and discharge events. So what we have to do is make sure that all these connectors are properly shielded, which means that the outsides of these BNC connectors are correctly connected to this end plate. These are cast end plates made from aluminum. And then there's a gasket in between these end plates and the actual body to make sure that there's no gap where something could leave or enter. That's on both sides. You could also do this with PCB designed face plates, which we will do in a future episode, I think. I'll leave it down below if you would like to see me design specific end plates that also fulfill the same purpose. Yeah. So now we can correlate ESD events to specific stuff. And we have two outputs. We have the actual pulse in the same waveform that it gets detected here. But also we have the digital output, which gives us a valid 5 volt 0 or nothing 0 or 1 signal at a 5 volt TTL logic level. So you can use this to trigger other devices like oscilloscopes or other circuits that you build. Maybe some specialized machinery, or you want to activate something based on an event. Which means that what we actually built here is a spark gap transmitter, which is highly illegal. Don't do that maybe, okay? For some weird reason, I find this oddly satisfying. Not just like using it, but actually building the thing, like making a deliberate circuit choice, integrating it into a professional case, making sure that everything works, and like it's a higher standard of building stuff. Test equipment is just stuff that really has to work and be well integrated to be useful, and I find a lot of joy in that. So maybe you would like to build your own specialized test equipment that you just can't buy off the shelf. Or maybe there is an option, but it's just prohibitively expensive. Let me know on the Element 14 community. You can also go there to download all the files for this so you can make your own. And I gotta go. There's another project waiting for me.